Let's say we have mass 6 kilograms that is attached to a spring that's got a spring constant of 20 joules per square meter. And let's say it's able to move around in the horizontal direction. Horizontal direction, if it's only moving horizontally, what does that mean we don't have to worry about? What can we ignore if it's only moving horizontally? Yeah, we can ignore potential energy of gravity because there's no change in height. So this will make these situations somewhat simpler to analyze. We don't need to worry about potential energy of gravity, but what should we consider as it moves around? What types of energy are going to be important here? Yeah, we're going to worry about kinetic energy because the object could be in motion. Thermal energy, I would really only expect thermal energy to play a role if what's happening. What's the only way kinetic energy might turn into thermal energy in this case? Yeah, if there's some friction, like if this object is scraping along the ground, and as the surfaces grind against each other, we're probably going to have some mechanical energy turning into thermal energy, or maybe even bond energy if something's at its melting point. But let's imagine that this object is on wheels or on a very slippery surface, so we don't have to worry about friction at all. Let's assume there's effectively no friction. We got kinetic energy possibly changing if this is changing speed as it moves around. Also, what other type of energy is going to change as this object moves? Yeah, specifically what kind of potential energy? Yeah, the spring itself is going to have spring potential energy, or sometimes called elastic potential energy. So as the object moves, if it's changing speed, maybe getting faster or slower, then its kinetic energy will be changing. So there's a delta KE. And as it moves, it's either compressing the spring or stretching the spring. So there's also a change in spring potential energy. And to keep track of that, we usually want to consider how far the spring has been stretched or compressed from equilibrium. There's some location, some length of the spring that's, I guess you could say, its natural length. That at that length, it's not exerting any force at all. That's its equilibrium length, where it would just stay if there was nothing pushing or pulling on it. And we typically call that x equals 0. So I'm going to use x here to represent how much the spring has been stretched or compressed. If the spring is at equilibrium, then it's not stretched or compressed at all, so x would be 0. If the object moves to the right, that's stretching the spring, so we'll call that the positive x direction. If you move to the left, you're compressing the spring, so we'll call that the negative x direction. So if x is positive, that means the spring is currently stretched longer than equilibrium. If x is a negative value, the spring is currently compressed shorter than equilibrium, just as our coordinate system. And we can also use that same coordinate system to keep track of where the massive object is, because it's directly attached to the spring. So let's say we start this system going by, how could you get this to start moving in the first place? What would you have to do to it? Yeah, you'd have to give it a push or a pull. And there are a couple of different ways you could do this. One way is from equilibrium, you could just give it a kick and just shove it so that it starts moving. That would be doing work to give it kinetic energy. As soon as it's got kinetic energy, it's going to start moving. And what does that kinetic energy then turn into? Is it just going to keep moving at that same speed forever, or does it slow down and turn into something else? Yeah, as it moves, it's compressing the spring. The spring being compressed means the spring is gaining potential energy. So that means the object is also losing kinetic energy. So as it moves, compressing the spring, it's going to get slower and the spring gets more and more compressed. Or alternatively, instead of giving it a shove, you could like grab it and let's say compress the spring, hold it still, and then just let go. If you compress the spring and then just hold it there, what kind of energy have you just given it? Right. By compressing it and then just holding it there, you've given it some potential energy, spring potential energy. If you then just release it, you haven't given it any kinetic energy. You didn't give it a shove to start it moving. You just let go. It's got lots of potential energy, but no kinetic energy yet. But the spring is pushing on it, so it's going to start moving as the spring's potential energy converts to kinetic energy, the object's motion. And so it's going to get faster and faster as it loses potential energy and gains kinetic energy. So to get this moving, you could give it a shove, assigning kinetic energy to it, or you could displace it and let go, assigning some potential energy to it to start with. Or you could do both. Maybe you pull this back, giving it some potential energy, and give it a shove, giving it some kinetic energy as well. So there are various ways you could give this energy to start with and get it moving to begin with. Any questions on that so far? So let's try a quick example. Let's say, just by way of an example, let's say you start this process by pulling this back. You pull the mass to, let's say you stretch it to a location that is 50 centimeters from equilibrium. And throw it towards equilibrium at an initial velocity of, let's say, 15 meters per second. So you pull this back, give it a shove, 15 meters per second. And let's say we want to know, presumably if you throw it, it'll eventually get to equilibrium. And we want to know how fast is it going when it passes through equilibrium. And let's say we also want to know, after it passes through equilibrium, how far will it compress the spring? What's the most it can compress the spring? So let's see if we can address both of these questions. First of all, if we're just going from the initial situation of, we know the starting speed and we know the starting displacement, 50 centimeters from equilibrium. And we want to know, for the final situation, how fast is it going as it passes through equilibrium? What types of energy are changing there? If we're going from far from equilibrium and moving at some speed to at equilibrium and moving at some other speed. Yeah, we're going to have spring potential energy changing. And also it's changing its speed. So we're going to be dealing with kinetic energy also. What's the usual indicator for a spring potential energy? Like, how do we know that spring potential energy is changing here? Yeah, absolute value of x, where x is where the object is. That is how far the spring has been displaced from equilibrium. And we typically write it as absolute value of x because we don't really care whether it's stretched or compressed. Both of those will represent the same delta or the same change of potential energy. And as it goes from 50 centimeters to equilibrium, what's happening to x? Yeah, absolute value of x has decreased, which in this case really just means we're getting closer to equilibrium. If you're getting closer to equilibrium from either side, you're decreasing the absolute value of x. So potential energy is decreasing. If you're moving away from equilibrium in either direction, then you're increasing the potential energy. So equilibrium is the lowest potential energy. If you get further from equilibrium, you're gaining potential energy. If you get closer to equilibrium, you're losing potential energy. And I think we even know the initial and final values. What are the starting and ending values of displacement in this case? Where does the object start and where does the object end according to what we're trying to find right now? Yeah, it starts at 50 centimeters. And the last position we care about in this in terms of this question is at equilibrium. As it's passing through equilibrium, its x value is 0. Although since the spring constant is given in terms of joules per square meter, we probably want to convert these to meters as well. So x initial is half a meter or 0.5 meters. And x final is 0 meters. As for kinetic energy, what should we expect to happen to kinetic energy during this time interval? Yeah, should be increasing. Presumably this is a closed system. The mass and the spring are interacting with each other, but there's no friction, no air resistance, no other work being done to or from this object. So I think we can assume that a decrease in spring potential energy is matched by an increase in kinetic energy, presumably because the speed of the object is increasing. We do know the starting speed, 15 meters per second. But we don't know the ending speed. We don't know how fast it's going as it's passing through equilibrium. Not open. You are doing work by pulling it back and shoving it. But the idea is that work was done before the time interval we care about. By specifying our time interval is from the instant you let go to when it passes through equilibrium, that means that the work was done before the time interval we care about. If we instead set initial is when it's at rest of equilibrium and then we start pulling it back and throwing it, then you're doing work during that time interval. But if we say we're starting our stopwatch at the instant you let go, then you've already done that work. That work is already energy in the system. So we don't need to include it separately as work being done to the system. Yeah, exactly. As long as we're careful to specify that we're talking about from the instant you let go onwards. So that's essentially taken care of is the fact that the system already has some potential energy due to its position and already has some kinetic energy due to its initial speed. That initial amount of energy is the amount of work you put into it. We don't need to separately treat it as work being done. Looks like the final speed is unknown though. That's really what we're trying to figure out. We want to know what is the final speed when it's passing through equilibrium. And as I said, we're assuming these are only interacting with each other, so we can treat this as a closed system. Any questions on that energy interaction diagram so far? So let's see if we can write that as an equation. It's a closed system, so the total change in energy better be 0, since there's no work or heat involved. And that total change in energy we can split up into potential energy change plus kinetic energy change. And what formula do we usually use for a change in spring potential energy? Yeah, that's going to be half the spring constant, the half ultimately coming from an integral, times the change in x squared. And I would be careful to write the x squared in parentheses and then delta that x squared. The idea being that we're squaring both the initial and final x values first, and then taking the difference. X final squared minus x initial squared. So it's the difference in squared x value. Much in the same way that change in kinetic energy is half the mass times the change in squared speed. So you're squaring the final velocity and squaring the initial velocity and then taking the difference. Those that are added to 0, And if we fill in some of these values, for instance, delta x squared can be written as x final squared minus x initial squared. And delta v squared can be written as v final squared minus v initial squared. And of these, which one are we trying to solve for? Yeah, we want to know what's the final speed. So this is what we're trying to find. And before we even plug in any numbers, we could solve this algebraically just in terms of the variables and then plug in the numbers at the very end. One exception, if one of the, or more of the values is 0, I would usually plug that in at the very beginning. But everything else, it's probably a good idea to leave them as variables until the end. So let's go ahead and fill in x final we know is 0. 0 squared is still going to be 0. So we get negative x initial squared times k over 2. Plus m over 2 times v final squared, which we know, minus, no, v final squared, which we don't know, minus v initial squared, which we do know. Also, both of these terms have a divided by 2. So what can we do with that algebraically? How could we get rid of both of those over 2 in one go? Yeah, let's go ahead and multiply both sides by 2 just to simplify things a bit. So 2 times the left side, 2 times the right side. That way we at least don't need to worry about the divided by 2. We've just got negative k times x initial squared plus m times, we'll go ahead and distribute that, m times v final squared minus m times v initial squared equals 0. And then how would we isolate v final here? Yeah, add these terms to both sides, so we get m times v final squared equals m times v initial squared plus k times x initial squared. A very useful way to think of this is that the mv squared term has changed. We started with a certain amount of mv squared. We're adding some change to it to get the final amount of mv squared. In fact, what would be our next step in isolating v final? What else do we still need to do here to isolate v final? We're going to take the square root eventually, but before we take the square root, yeah, I would start by dividing both sides by n, just due to order of operations. The squared is the first thing being done to be final, and then it's being multiplied by n. We want to undo that in opposite order. So divide by m first, and then take the square root. So if we divide both sides by n, on the left side, the m's cancel out. On the right side, we're dividing both of these by n. So on one term, it cancels out, but the other term still has a divided by n, because we're dividing the whole thing by n. So again, we could think of this as a change, specifically a change to v squared. We start with a certain squared speed, we add a change to it, and we end with the final amount of squared speed. So the k over m times x initial squared represents how much the speed squared is changing. Not how much the speed is changing, but how much the squared speed is changing. At this point, we can go ahead and take the square root and get v final equals square root of v initial squared plus k over m times x initial squared. So this gives us not just a single number, this actually gives us a formula for the final speed depending on whatever initial speed and initial position we started with. Any questions on that so far? So that will tell us the speed as it passes through equilibrium. Although formally, anytime you solve an equation by taking a square root, what else should you include in your solution? Yeah, we should include a plus or minus. For instance, if you knew that, let's say, x squared equals 9, x could be 3 or x could be negative 3. The plus or minus in this case, though, what do you suspect a plus sign or a minus sign represents in terms of speed? What would that signify? Yeah, that's all about direction of travel. If all we're saying is we want to know how fast will it be going as it passes through equilibrium, it might be passing through equilibrium towards the left, or it might be passing back through equilibrium towards the right, because this is going to be oscillating. So the final speed we get, the solution for that, ends up having a plus or minus, because we haven't really specified in the equations which direction is traveled. So if you happen to know which direction it's traveling, you can fill that in manually. You can choose a plus or a minus based on direction. Or if you just want to know how fast it's going, you could treat this as an absolute value. But we now have a formula for how fast it's going. We could even fill in the values for 15 squared plus k over m, so 20 over 6 times x initial, so 1/2 squared. So filling that in, we get v final equals square root of 15 squared, so that's 225, plus k over m, 20 over 6, times x initial squared, that's 1/2 squared, so 1/4. So 20 over 4 reduces to 5 over 1. So 225 plus 5/6, and then take the square root. Let's see what that actually looks like. 225 plus 5/6, and take the square root. And it's pretty close to 15, just 15.03. So as it goes from 1/2 meter to equilibrium, it's speeding up very little by comparison with the initial speed. Largely just because this is a very weak spring. 20 joules per square meter is very, very weak for a spring. As opposed to if the spring constant had been larger, we'd be adding a larger amount to it. Or if the mass had been smaller, we'd be adding a larger amount to it. So each of these values influences the final result. Any questions on that so far?
I'm sorry, just really cramped up at some point. So second to last, it said VF squares equals VI squared. I just can't read the rest. I'm sorry.
Yeah, V final squared equals V initial squared plus K x initial squared over n. So we added this term to the other side, and then we divided the whole thing by n. So we get the kx initial squared, but on the other side, and divided by n, because we needed to cancel out this times n.
And there's a cubed in there, if I'm reading it.
Squared. Because this was originally k times x initial squared from the original formula for spring potential energy.
I'm sorry, my internet's just slow, so that everything looks pixelated. Thank you, though.
Any other questions on that so far? Alternatively, if we want to know the other question, what's the most it will compress the spring? We could use most of the same setup. We're still starting at 1/2 meter. We're still starting at 15 meters per second. But now instead of ending in equilibrium, we're looking at how far it goes in the other direction, beyond equilibrium, which means we don't know x final. So for this version, what's the most it will compress the spring? We can use a lot of the same setup, but we're changing some things. X final is going to be some unknown value. And also, if we're talking about the most it compresses, what's the final speed going to be? If we want to know the furthest it can get. Yeah, the furthest it can get has to be final speed 0. Because if the final speed wasn't 0, that means it would be still in the process of moving. If we want to know what's the furthest it can get, that's where it comes to a stop and is about to turn around. So if we want to know the furthest it can get, we should assume V final is 0 at some unknown location. So we'll replace V final with 0, which means actually what has happened to the kinetic energy. Yeah, the kinetic energy overall has decreased. It has slowed down overall. It is getting faster and faster as it goes towards equilibrium, but then afterwards it gets slower and slower and eventually comes to a stop. So overall, from initial to final, the speed has overall decreased. So we've lost kinetic energy and therefore presumably gained potential energy. It's going to end up further than half a meter from equilibrium. In fact, probably a lot further. And we can use most of the same setup. We can still use change plus change equals 0. These are still going to be k over 2, but we can multiply by 2 anyway, times unknown x final squared minus x initial squared, plus m over 2, but we're multiplying by 2, so that cancels out, times v final squared, which in this case is 0, minus the initial squared. So again, we could use, write it out the same way. K times x final squared, distributing the k to both terms, minus k times x initial squared. And then m times 0 is 0, m times negative v initial squared is minus m times v initial squared equals 0. And in this case, what are we trying to solve for? Yeah, we want to know x final. How far does it get from equilibrium? And we can solve this mostly the same way. Add these terms to both sides and divide by k. So we're going to get k x initial squared on the other side, but we're dividing by k, so we just get x initial squared plus mv initial squared divided by k. So mass over spring constant times v initial squared. And then once again, we take the square root, cancel out the squared. And technically also a plus or minus, because it could be this far on the compressed side, or when it bounces back, it'll get that same distance on the stretched side. So it could be either one, but we're specifically looking for compressed. So we'd be using the negative value if we needed to specify. And we can now plug in those numbers. We know x initial is 1/2. So 1/2 squared is 1/4. M over k would be 6 over 20. Times v initial squared is still 225. So 1/4 plus 6 over 20 times 225. And I'm getting about 15 meters. So it ends up about 15 meters from equilibrium. You pull this back, give it a throw, it ends up about 15 meters away from equilibrium. Any questions on that so far? And note that it kind of takes a while to analyze this. If we were looking at just one single data point that we wanted to figure out, it doesn't take all that long. You set up your equation, solve, and you're done. But if you're looking at another data point, you basically have to do that same thing all over again. And the more data points you're looking for, the more extra calculations it's going to take. So this approach of setting up an energy interaction diagram, solving for some unknown final value, this is really only all that useful if you're just looking for one more or a few more pieces of information. But it ignores everything that happens in between. If you do care about what happens in between, graphing the energy can be a much better approach. So let's try looking at this same situation, but with an energy graph instead of just looking at individual data points. The idea is we're going to make a graph of position versus energy. We want a little space there. Position versus energy. So position is going to be marked as X. And we found that it only goes to about 15 meters. So it's going to compress up to about 15 meters and it's going to stretch up to about 15 meters. So let's mark, maybe mark this in 5s. And then we can calculate how much energy is involved. Since we're going to be making a graph, it's often a good idea to sketch out a data table. And what we care about is X, the potential energy of the spring, and the kinetic energy. And since it's a closed system, we also should investigate the total energy, since that should be a constant. And let's try several different X values. We know 15 is going to be important. Since that's the furthest it gets to the right. We also know negative 15 is going to be important since that's the furthest it gets to the left. And let's try calculating some of those values. At X equals 15, what's the spring potential energy? Or how could we calculate the spring potential energy? If we fill that into the usual formula, K, what half the spring constant times X squared, we've got a spring constant, 20 joules per square meter. We've got a X value, X is 15 when it gets the furthest from equilibrium. So we can multiply that out. 15 squared is 225 times half of 20, so that's 225 times 10. So 2,250. Meters squared cancel out, so we end up with joules. So that's the potential energy at both 15 and negative 15. Also, if 15 is the furthest it gets, what's the kinetic energy at that location? Yeah, should be 0. If it has reached 15 and come to a stop, then the kinetic energy is 0 at both of those locations. And the key to this entire graph idea is if we know all the types of energy at some specific location, what can we now find? What would you get if you add those together? Yeah, that's going to be E total. So in general, if there's any one location where you know the potential energy and kinetic energy, and maybe any other energies that are involved, you can add those values to find E total. 2250 plus 0 is 2250. And since we're assuming this is a closed system, what was the value we got for X final? That was the 15 meters from equilibrium. So in the situation we were dealing with, we found that it'll get 15 meters from equilibrium before it comes to a stop and bounces back. Which is why I think it's a good idea to use that as one of the X values we care about as we're setting up the graph. Because we know that at that location, it comes to a stop. So kinetic energy at that location will be 0. Alternatively, you could use the initial conditions. We know that when X is 1/2, we have a certain speed. That was what? 15 meters per second. So you could fill that in as well. In this case, though, the fact that we know that at 15, it's at a stop, I think that's going to be easier to use, just in terms of making the numbers easier to work with. And if we know E total at this location is 2,250, what do we know about E total everywhere else? Yeah, also 2250. This is probably the most important single piece of information about any closed system. That if you know the total energy at one location or instant in time, it's going to be that same value everywhere else. So no matter where we consider on the x-axis, E total is always going to be 2250. And that means we can figure out a lot of other information. Let's try some other data points. What would be another x value we should care about here, just to get some more information? What would be another x value that would be useful to graph?
Maybe the halfway point,
The halfway point. So specifically x equals,
10.
sure, let's try x equals 10.
Oh, wait, that's not the halfway. That would be 7.5.
Well, I mean, it's partway there. Let's go ahead and try 10. I mean, that's going to be an easy number to use in terms of the calculations. And it does give us one more data point on the graph. So if we fill in 10 for x, potential energy, we can actually just make try to think of potential energy as a function. Potential energy as a function of x is half the spring constant times x squared. The spring constant is 20. 20 over 2 would be 10. So in general, the spring potential energy in this situation is always going to be 10x squared. So for any x value, you can just square it, multiply by 10. That's going to be your potential energy in this situation, at least. So 10 squared is 100 times 10 is 1,000. In fact, we could fill in a variety of other values. Perhaps most importantly, what other x value is going to give us the exact same potential energy?
-10.
Yeah, -10, because x is being squared. It doesn't really matter if we use 10 or -10. In fact, I'm just going to write a plus or minus here. Whether x is +10 or -10, we're going to get the same result. 1,000 spring potential energy, 1,000 joules of spring potential energy. And let's fill in a couple other values as well. Let's say 5 or -5. Again, it's not going to matter whether it's positive or negative. If we fill in 5 or -5, and again, the potential energy is going to be 10x squared. If we think of spring potential energy as a function of x, that's 10x squared. So you fill in 5 for x, and what do you get as a result? Yeah, 5 squared is 25, or -5 squared, also 25, times 10, 250. And let's also throw in 0. If x is 0, what's the spring potential energy going to be? Yeah, also going to be 0. And just for comparison, even though it's outside the range of actual motion, just to see what happens mathematically, let's throw in, let's say 20 also. If x is 20, what would the potential energy be? Right, 4,000. And we could graph this. This is potential energy as a function of x. We've got a bunch of data points. We could plot these on the graph and connect them with a curve. So let's try that. Looks like energy goes up to 4,000. So I'm just going to mark this in units of thousands. So 1,000, 2,000, 3,000, 4,000. So plotting these, we've got when x is 0, potential energy is 0. When x is 5 or -5, potential energy is 250. When x is 10 or -10, potential energy would be 1,000. When x is 15 or -15, potential energy would be 2,250. And if we took this further, if we go all the way to 20, if x is 20, which it won't be, but if x were 20, mathematically, we would expect potential energy to be 4,000. And what shape are these points forming? Yeah,
A
we've
U
got
shape.
this- Sorry, what was that?
A U shape, a parabola.
Yeah, we do get at least it looks like a parabola. And I think mathematically we can say it genuinely is a parabola. Because what do you notice about the function that created this in the first place?
It's exponential.
Not
It's a square. It's a squared
exponential.
one. I mean.
Yeah, exponential function would mean some constant to the power of x in the exponent. This I would call a quadratic function in the sense that it's the variable to the power of 2. So x has been, the old-fashioned term would be that this is the quadrature of x, which is why we call it a quadratic function. Quad is in square. So since the function has an x squared and no higher power of x, we're going to get a quadratic. Well, it's a quadratic function, meaning the parabola is the shape. And that's specifically because we're graphing x versus x squared. We could also graph kinetic energy as well. We know a couple of data points for kinetic energy. We know when x is 15 or negative 15, the kinetic energy is 0. So we label this potential energy. How could we find some other values of kinetic energy? Like how could we find the kinetic energy when x is 10 or negative 10? Yeah, we know that potential energy plus kinetic energy still has to add up to 2250. So we could subtract total energy minus potential energy to find kinetic energy. Algebraically, that's going to look like kinetic energy plus potential energy equals E total. So kinetic energy equals E total minus potential energy. So subtract 2250 minus 1,000 is 1,250. So at 10 or negative 10, kinetic energy is going to be 1250. Let's plot that on the graph. 10 will be at 1250. Negative 10 will also be at 1250. Or if we fill in 5 or negative 5. Again, E total minus potential energy, that's 2250 minus 250. So we're left with 2000. So at 5 or negative 5, the kinetic energy must be 2000. 5, 2000, negative 5, also 2000. And lastly, when we're at 0, there's 0 potential energy. So what does the kinetic energy have to be? Yeah, 2250 minus 0 is still 2250. I guess I should fill these in as well. So we can fill that in. When x is 0, kinetic energy is 2,250. And also, if we went one step further, when x is 20, potential energy is 4,000. So what would kinetic energy have to be?
Negative 1750.
Yeah, negative 1,750. And why is that a problem? What should we expect about kinetic energy values?
They should, for the most part, at least this portion, it should always be positive.
Yeah, well, positive or 0. It's okay for kinetic energy to be 0. That just means the object has at that location come to a stop. But kinetic energy can never be negative. Because if we go back to the original formula, v squared is always going to be positive unless speed is imaginary, which doesn't make any sense. And m over 2 is always going to be positive unless the mass is negative, which doesn't make any sense. So there's no way you can get a negative result for kinetic energy if you're using actual real world values. You can get 0 if the object comes to a stop, but a negative value for kinetic energy does not make any sense. And ultimately, this just means that the object cannot reach this location, at least not at this total energy level. You could get it to this location by adding more energy. But at this total energy, 2250, the object cannot reach a location of x equals 20. We could, however, connect these points. It looks like these points also form an upside down parabola shape. And the reason those are related so closely, it might help to think of this not as E total minus potential energy, but as negative potential energy plus E total. Think back to algebra. If you have a function of x, because potential energy is a function of x, and you apply a negative sign, what does that do to the shape of the function? Like if you're graphing 10x squared, but then you change it to negative 10x squared. Yeah, that's going to flip it. Specifically, it flips it directly across the x-axis or the horizontal axis. So potential energy squared is this upright parabola. Negative potential energy would flip it to be an upside down parabola. But then we also add E total. What happens to a function if you add a constant? What would that do to the graph?
It moves it upwards or downwards.
Exactly, we get that vertical shift. So negative potential, so potential energy is this parabola. Negative potential energy flips it across the axis. And then plus a constant shifts it. And there's your kinetic energy curve. So the kinetic energy curve, assuming there's just kinetic energy and one form of potential energy in the system, and it's a closed system, the kinetic energy graph is going to be the potential energy graph mirrored across the axis, shifted up or down based on E total, and of course cut off at 0 because you can't have a negative value for kinetic energy. But in general, in any case where there's just potential energy and one form of kinetic energy, the kinetic energy graph should always look like a mirror image of part of the potential energy graph. Flipped, shifted by E total, and then cut off at the axis. So that would be our potential energy graph formed by the formula for that type of potential energy. The kinetic energy graph either flipped and shifted or plotted point by making these calculations. And also if we graph E total, what would that look like on the graph? If E total is the same value everywhere, what shape would that form? That's a constant, so its graph would look like, right, horizontal line at 2250. So this would be E total, just a flat horizontal line. And this tells us all the information we need about the system, really. Then instead of just having one initial value and one final value as information, we can now use this graph to get information about any x value. Like if we wanted to know how fast is it going when it's at 7 meters. If we take a look at 7 meters, we could look at just this cross section of the graph. And we'd have a value for potential energy, whatever that is, and a value for kinetic energy, whatever that is. And then you could set that kinetic energy equal to 1/2 mv squared and solve for speed. So the graph shows not only one initial value and one final value, the graph shows the kinetic and potential energy at any location you want. And of course, you'd need a very accurately labeled, a very accurately drawn and well-labeled graph in order to get very useful information numerically. But really the important thing is that the shape gives you information about the behavior. Then based on the kinetic energy graph, we know it comes to a stop at 15. It comes to a stop at -15. It's going fastest as it passes through equilibrium, and it should be oscillating back and forth between those values, oscillating within that range. Any other questions on that? So try this out on your own. Try maybe a different type of energy, maybe gravitational potential energy instead of spring potential energy. Try this same sort of approach, assuming you have some initial values of speed and position. Make a graph of position versus all types of energy that you care about. Draw out a data table if you have specific values to work with. Plot those point by point on the graph. And consider as you're doing this, how are the kinetic energy graph and the potential energy graph related to each other? So try out some more examples of that. Let me know if you have any other questions, and I will see you next time. You're welcome.